So this is a continuation of exponents and their properties. So we have looked at solving, undoing something to the fifth power, the third power, and so on in our first video of this chapter. Now we're going to go back to something that's hopefully familiar to you, and that is our exponent rules. So like bases, all the things that we can do with them, we're going to look at now with all of these powers, fifth power, third power, fractional powers, and so on. So remember, like bases, we multiply them, add the exponents, power to a power, we multiply the exponents. If I have two pieces raised to the same power, I give that power to everything, and negative exponent, 1 over, and so on and so forth. So hopefully this is something that you remember. So now we want to look at, let's look at our examples here. So we've got example A, and it wants us to simplify 7 to the 1/4 times 7 to the 1/2. So that is 7 to the 1/4 plus 1/2. Okay, so that's 7. So I got to add those exponents. So I've got 7. If I make a common denominator, I've got 1 over 4 plus 2 over 4. So that's 7 to the 3/4 power. Now, yes, I could write that in the radical form, but I don't need to right now. Okay, part B. We've got two pieces in here. They're not like bases, so I cannot simplify within here, but I'm raising both of them to the second power. So that means I need to give the second power to both. So that's going to be 6 to the 1/2 times 2 and 4 to the 1/3 times 2. So that's overall 6 to the 2 over 2, which is 1, so that's just 6, and 4 to the 2/3. That does not become 24 to the 2/3. I can't, because these are unlike bases, I can't combine them. All right, now let's look at 16 to the 3/4 times 16 to the 1/2. So again, I'm going to add the exponents. Okay, so if I add the exponents, I've got 16 to the 3/4 plus 2/4, which is 16 to the 5/4 power. Now, technically, what that means is I have 16 to the 4 over 4 times 16 to the 1 over 4. So I could treat that as 16 times 16 to the 1/4 power. Let's change colors here because it's getting a little... All right, let's go red. All right, so now I've got like bases divided, so I subtract the exponents. So I have 6 to the 1 minus 1/3 power. 3 over 3 minus 1 over 3 is 6 to the 2/3 power. And last but not least, first I'm going to give the second power to both pieces. So I've got 42 to the 2/3 power over 7 to the 2/3 power. Now, because these are not like bases, I cannot do anything more with it. This does not become 6 to the 2/3 power. It stays where it is. And that was a really quick review of power rules. Okay, now if you remember too, back when we did square roots and simplifying square roots, such as the square root of 12. So if I did the square root of 12, we would break that into two factors where one was a perfect square. So I did square root of 4 times square root of 3, and that became 2 root 3. We're going to do the same thing, but have to do it with any of these roots. So instead of a perfect square now, I want to look at perfect fourth powers. Okay, so this is going to get broken into the 4th root of 16 times the 4th root of 81. I can split this up. 4th root of 16 is 2. The 4th root of 81 is 3. So I get 6 overall. Okay, when I have the 5th root or any root of a fraction, I can split that into the 5th root of 243 over the 5th root of 32,768. Now, I wouldn't expect you to know that the 5th root of that number is 8. we're going to make a chart so that you have some of these. And the fifth root of 243 is 3. So I get 3/8 overall. And then for this last one, honestly, this is a perfect cube. So yes, I could split it up kind of like we did in part A, but I would just know that the cube root of this number is 18. All right, so let's practice a couple more. Okay, so we've got the square root of 98. So I need to split into perfect squares. 98 can be factored into 49 times 2. So the square root of 49 is 7 times square root of 2. Okay, now the rest of these aren't square roots. I've got a cube root for b, so I need to look for perfect cubes. So I've got the cube root of 32 times the cube root of 25. 32 times 25 gives me 800. Sorry, I'm thinking fifth root. I want cube root of 8 times cube root of 100. Okay, so cube root of 8 is 2. Okay, cube root of 100. Now, I need to know, is 100, does it have any factors itself that are perfect cubes? Like, can I do 8 again? Can I do 3 cubed? 27? I don't think so. Can I do 4 cubed? And so on and so forth. It doesn't look like it has any perfect cubes, so I'm going to leave it as 2 times the cube root of 100. Okay, I'm going to do one more. Let's do C. Let's go ahead and just do C. So I need perfect sixth roots now. So I've got sixth root and sixth root. Okay, so I need one that 1458 factors into where 1 is a perfect sixth. So if I did 729 times 2, okay, so sixth root of 729 is 3. And I can't take the sixth root of 2. Now, how I do this, so when we make our chart, I'm just going to start dividing 1458 by perfect sixth until I find one that works. Okay, so that's kind of how I do, that's the method to my madness. So I want you to try a couple more of these for yourself so that see how you're doing with this. So in conclusion, just a quick recap of what you've watched. I know I haven't finished all these notes. We're going to do the last page in class when I see you. We need to remember our exponent properties, right? And it has to be with like bases. If we can't simplify if they don't have like bases, but I can raise a power to a power. It just means that I can't divide and things like that. We also need to remember how to break down into perfect factors. So we looked at, taking the fourth root of a number. So I need to break this number into a perfect fourth root and a times something that's not a perfect fourth root so that I can simplify and leave this one alone. And you keep going until you can't simplify it any further. But it doesn't matter what this root is. It could be 5, it could be 10, it doesn't matter. We break it into perfect roots where one of the factors is a perfect root and one is not. We're going to practice this a bunch. Okay, yes, you will have a calculator for some of these problems, but we kind of want to just get the hang of how these things simplify so that when we're doing calculations later on, it makes a little more sense to you as to what the calculator is doing and why you're getting the answer that you're getting.